next item on the agenda is a short panel on theory. So we'll have Ben Recht, he's in the room, and Julia Kempe, and Eero Simoncelli. Can I invite you over? Thanks.
No. In the end, you guys sit there. There we go. Like this timer.
Where's the? I mean, we should shorter than.
We can go as short as
We should go shorter. I mean, this question doesn't require us.
So apparently Julia has a strong opinion here that says that this shouldn't take very much time. And the topic of this panel is, can better theory have an impact on practice in deep learning? So Julia, I think you already, Julia Kempe from NYU has opinions, and so please share.
Yes, so when I was asked to be on that panel and I looked at the question, it seemed like a complete no-brainer. Obviously, the answer is yes, and we can just go home and be done. Then I looked at the question more clearly, and I think here the question, we need to tease it apart into two pieces. What's a good theory and what's practice? And we've heard wonderful talks this morning that spoke about what good theories could be. So I'm not going to dwell on this very much. But there are various flavors of theories, right? There is, for instance, the more applied theories, if you wish, where we study trade-offs. How much width for how much depth, for how much, renormalization of the parameters. Then there are theories that are, more perhaps fundamental, whatever. What happens, physicists like to do this a lot. What happens in the infinite limit? Width goes to infinity. Every parameter is Gaussian. What can we say? And then, yes, we see a phase transition. So these are very nice theories. There are other theories. Generally, we have a trade-off in theory space, I think, between a general theory and an expressive theory, as often. For instance, we know that it's NP-complete. Nati said that very nicely. It's NP-complete to solve the problem with two hidden units. That's a wonderful theory, and nonetheless, in practice, probably completely irrelevant. So in that sense, it is important to ask the question, if we care about practice, we have to perhaps understand better what the practitioners care about. And at the Center for Data Science, at least, we have on the order of nearly 300 master's students, which try to, study deep learning, machine learning, etc., and then they want to get a job. And I can observe them, at least, because they do capstone projects, they build all these things while they study. I can observe what they care about. And I also, I just maybe want to preface it. I saw recently a panel with Jan LeCun on it. I saw it on YouTube. It's probably older than that, where he was asked a similar question. It was more like, do we care about deep learning being interpretable? And he took the other perspective and says, no, we don't care about it. If I go, he has a work with economists on real estate pricing, and he built some system for them, and they can estimate real estate prices in Los Angeles. And he said, if I tell them now that the system has to be changed slightly, and it will take longer, and we need more parameters, and so that it can be interpretable, they're just going to walk away from me. They don't care. And so, in that sense, there are lots of things that our students don't care about. What do they care about? They care about compute, I think, how much compute they have to use to get their results. So in that sense, it would be good for us to understand, trade-offs between width and depth and so on. So this is the kind of practical theories that practitioners would care about. They care about the amount of data that they have to use. So in that sense, yesterday we heard that a lot, the n=1 problem is relevant for them as well. They do care also about instabilities to some extent. They care about, how to optimize. But in the end, it's true that they are still in the soup stirring. Who said that about the soup? Who said about the soup? No, Ali today. So in that sense,
Croutons.
Croutons, right. So they are very much in crouton mode. And for them, really, I think a lot of the stuff we consider theories is relatively unimportant, I have to say.
Eero?
Well, let's see. I guess I said to David about a half an hour ago that this question is either something you answer in 1 minute or you answer in several days of discussion. So I guess that's what our meeting is about. I'll just try to say a few things that maybe are complementary to what Julia just said. So on the engineering side, it seems to me that, we have a long history of building engineering tools. What does it mean to have a good tool for engineering or toolbox? And you think of linear systems, you think of Gaussian processes, things like Markov random fields, things where we have developed both intuition and a set of rules and a logic that allows us to connect the ultimate capabilities of systems with the sort of components that we have to deal with when we design them, because by necessity we have to design these things in a sort of modular form, to break down our problems into pieces. And in order to make the tools useful, we need to understand what each of those pieces does. We need to understand the rules that govern situations under which they work or don't work. We have to know the sort of operating range. And those are the things that go into engineering tools traditionally. And so it seems like what do we need? If we want to use deep nets as a tool, are they an engineering tool, and or if they're not, how can we make them into one? In some sense, Jan's comment that Julia just repeated, that we don't need interpretability, I guess from my perspective, it depends what you mean by interpretability. I think what we need is a way to translate between the goals that we have of solving a problem into the rules for designing the system. So we have to understand how to choose all of those things about the architecture, how to choose the local rules that are used in the architecture. We have to know how to choose an objective function. We have to know how to choose a training set, because that's an important part of the problem. And we have to know how to choose an optimization procedure, which maybe induces a lot more onto the solution than we previously expected, as we heard about this morning. So, and I think most of those things we don't have right now. We know what the basic unit is, a linear thing with a rectifier. Well, that's something that linear things we've known about for hundreds of years. We know how they behave. That's a perfect tool for an engineer, understanding what a linear system does. The idea that superposition, this very abstract principle, leads to the formulation of a linear system, and those two things are sort of synonymous. There's a concrete instantiation of an abstract concept, and we use that both on the practical side of designing things with those tools, and also to make abstract inferences and have an understanding about what that tool can do. And I think I think many of the people in this room realize that that's what we need for a deep net. We need a connection between abstract principles, which would be things like geometry, invariances, the kinds of things that we would like to induce or put onto a problem that we're trying to solve in engineering, and well, how do I design this network to make sure that it comes out that way, having these invariances? The adversarial examples are just examples of catastrophic failures of invariants that we didn't expect, because these solutions were working so well on the things that we train them on and test them on. So that's my overall comment about the engineering side. And of course, then there's the science side. Are these things a good model for the brain? And I think the answer is, as they stand, no. They're a very primitive model for the brain, or for, let's say, perceptual systems, sensory systems. And what do we need there? Well, we kind of need the same things. We need tools for probing and understanding these systems, and we need also theories that are going to generalize way beyond rectified linear units to things that have more complex computational capabilities, but that are still cascaded and built into recurrent circuits. So on the neuroscience side, I think we need a much, much richer theory that would be way beyond what I was just describing for just the sort of practical engineering side of how to use a deep net to solve an engineering problem.
I want to come back to, or relate to what Eero said a little bit, because I was a bit cynical by saying they don't care that much. But if it goes further, there is more and more, of course, deployment of deep learning or any machine learning algorithms out there, and it starts to become an issue also of, I mean, you all heard the examples of having machine learning used in the judiciary system and trying to understand then whether the algorithms are biased or not biased. All that work is, of course, it becomes more and more important. And so I quoted Jan, but I don't agree with Jan, I should say. I'm just reflecting what a lot of people as practitioners think. I do believe that the theory is becoming increasingly, especially interpretability, is becoming increasingly important once it becomes an issue of politics and regulation and sociological issues. That's obvious. There's another interesting thing that in the sciences, I mean, in Eero speaks about neuroscience. I see it in biology and physics. More and more of these tools are used rather blindly, but interesting new physics comes out of it sometimes. And so physicists, or I guess also biologists, I'm less connected, start to ask the question, why can this thing predict the dynamics of such and such system better than we could? And so, of course, understanding the theory might, if you view scientists as practitioners in that sense, might give us new insights into actually science and even physics on how information can be represented or compressed, etc. So in the end, I think the answer to this question is of course a resounding yes, but it's not something we can discuss, I think, in 5 minutes.
We do have 2 minutes for questions, though, so if anyone would like to ask something of the panel.
We were hoping maybe that Ben would comment on some of the things that he obviously has on his mind, and that then Julia and I could serve as moderators.
Exactly.
Go ahead, Ben.
All right. Right. All right, I have two things quickly. I do think that theory has failed time and time again to understand how to communicate guidelines to practice. I feel like even if we know we're right somehow, the failure of communication is as fatal as being right. I mean, just being right and not being able to tell people is incredibly dangerous. What I would hope a science of deep learning could do would be to provide guidelines to engineering practice, as all science does. And the reason why I think that's important is because, as Julia said, we've deployed these things in all sorts of systems where people's lives are now at stake. It's much more serious. I actually think it's much more serious than we give it credit to. And while it's fun to talk about the various generalization bounds we want to derive, we are at the same time letting people die in self-driving cars. We are letting people get discriminated against in terms of whether or not they are released from jail. We are letting companies deploy systems that bias against different kinds of candidates. And these are all using machine learning, some of it deep, some of it shallow. And I think what's interesting about having this in Washington is I do think that at some point it's not enough for the scientific community to be involved, but there have to be policy decisions made, and we have to be able to inform them. And I guess our challenge is, both as practitioners and theorists, is to be able to speak this in a clean way that sometimes loses precision when you move from equations to trying to communicate and trying to understand how much precision we can lose and still communicate these issues clearly and cleanly. We have like 1 minute, and there are 3 people who want to, so you guys want to, go ahead.
I'll be controversial. I would say that theory can sometimes be harmful to practice, because theory sometimes says you can't do this, or you can't, this is NP complete, even an approximation. But sometimes people see that and say, okay, I'm not going to even try. But the hard part are these pathological cases that the real world is more coherent and more reasonable, and those are rare things that we don't really have to worry about.
Right, I think Julia did make a similar point. I would just say this, in terms of deep learning, I feel like theory has had no impact whatsoever, so it's fine. They can say whatever they want, and no one listens.
No, they say in theory and practice are the same. In practice, they are not. I think people are very aware of this in practice.
But I think perceptron is a good example of that. Okay, linear single-layer perceptron can't. There's this huge class of problems that we can't solve, and okay, well, don't bother with those.
No, but I think that's the great example, because again, nobody cares. And honestly, I think most of the people doing deep learning don't even know that result. And I think it's
people did care.
I would say the large majority.
It did, for a period, suppress research and thinking about the problem, so I think your point is well taken. But clearly now, there's nothing holding anything back.
Okay,
On
with
the
that,
contrary.
we should wrap up because we're running a little late. I'd like to thank Julia and Eero again.